All right, very good. So let's start where we left off. So last week, we basically covered the basis, the fact that superconducting, you shouldn't think about superconductors like normal material. You should basically forget everything you know about your electrons physics, because now you're dealing with the bosonic condensate. And the thing about the bosonic condensate is that, well, it's a macroscopic quantum system. That means that you could reduce, all the Fermi electrons, 10 to the power of 20 electrons, you could just reduce that into one pair of electrons. Because the wave function of these two, a superconductor the size of this room, and a single pair of electrons, their wave function, their symmetry is identical. So that's the nice thing about superconductors, and also the confusing thing about superconductors, because we're so used to thinking about, with this microscopic picture of particles and in a lattice and that, Fermi electrons, that sort of thing, that we kind of, it's a bit of a transition to go from that to a macroscopic condensate, like a superconductor. But that's what this course is about, so that's what we're going to cover. Right, and so the thing that it happens is that, of course, at the transition, normally you have Fermi electrons. So these are the electrons that do all the work. So those Fermi electrons that are responsible for electromagnetic, optical properties, everything that basically happens in matter is mostly, they're responsible for that. So those Fermi electrons are now transformed into Cooper pairs. And what that does is that it actually opens up a gap at the Fermi surface. So where you have electrons are now, there are no electrons, only Cooper pairs. So in a way, the gap is similar to what you have in a semiconductor or an insulator. The difference here is that, well, it's not empty, it's just full of paired electrons now. And within that gap, there is no high energy Cooper pair or low energy Cooper pair. There's no hierarchy between these Cooper pairs, basically. So that's last lecture. Then we went on to look at the quantum mechanical description of superconductors. So we looked at the Ginzburg-Landau formalism, which is the equivalent of the Schrödinger equation, but with a nonlinear term, and which most of the time you can ignore, and you'll see why in your homework. So you have the Ginzburg-Landau, which is basically, instead of E, now you have this alpha, that's your eigenvalue. E is actually 2 electrons, the charge of Cooper pairs, M is 2m. There's a one-to-one basically correspondence there. And then there's a second equation, which is very important, the London equation, which describes, the supercurrent. So the first one is mostly about the amplitude of your wave function. This one is more about the dynamics. And you can see that it basically have the supercurrent and it has magnetic field. And the gist of it is that basically that in a system where you have supercurrent, the thing that drives the supercurrent is what? Does anybody remember? Anyone remember what?
Phase.
The phase, the gradient of the phase. So if you have a phase gradient, that's what drives a super. That's how you get a supercurrent. Because by definition, in a superconducting system, there is no voltage. There is no potential difference. So the thing that makes your supercurrent to go from point A to point B, the charge to go from point A to point B, is the gradient of the phase of your macroscopic wave function. Okay. Then, very important, and this is what we're going to continue in this lecture, is the fact that, we said that you can reduce your whole system into one wave function, and it doesn't matter. Your wave function stays the same regardless of the size of your system. But there's still two length scales that you should keep track of, and those are the length scale for the amplitude of the order parameter and the phase of the order parameter. Now, because each of these can vary in space and they have their own characteristic length scale. They're independent of each other. So the amplitude of the order parameter, which you can also think of as Cooper pair density. Some people also call it the size of the Cooper pair, and I think, you know, in some cases that analogy sort of makes sense. But what it is that it tells you how quickly the amplitude of your wave function can vary in space. So, for instance, here you have a superconductor. This is maximum amplitude here. But then you have an interface with a normal metal. Eventually, this thing has to be metallic, otherwise everything would be superconducting. So here, your amplitude is 0, and here is maximum, and you see this length scale over which your order parameter decays, that's your coherence length. And it's material dependent. So for instance, in the superconductor, your coherence length is different from the coherence length in a normal metal. So that's what a coherence length means. Any questions? Yeah? This is all clear? Good. So this deals with the, you know, how stiff is your the amplitude of your order parameter. Now there's the second one, which is lambda, the magnetic penetration depth. Now what I prefer actually is to call this phase stiffness. Why? Well, because, I mean, I'll tell you what. First of all, why we call it magnetic penetration depth? Because it's the, you know, it's a length scale over which your magnetic field decays inside the superconductor. So here you have a superconductor, you know, here you have external magnetic fields, and this field decays over this lambda, you know, what we call a London penetration depth. Because eventually, if this is, for example, bulk superconductor here, it would be 0, and this is your decay. Now, what's the link between phase and magnetic penetration? Can anybody tell me how these two are connected?
Phase drives the screen current.
Yes. So, exactly. I mean, think about it. How do superconductors screen magnetic field or expel magnetic field? They generate the current. They have a current, and this screening current is what actually counteracts the external magnetic field. And as I said, to have a supercurrent, you need phase grading. You need a variation in the phase of your wave function. So the length scale over which you can actually have your phase varies is the same length scale over which supercurrents vary, you know, and also this length scale for, you know, screening magnetic field. But, you know, you know, but the essence of it, I think the best way to think about it is as a length scale over which you can have currents. You have a maximum current here and 0 current here. That's the length scale over which, you know, your currents decay or your phase changes. Okay, so the thing to remember is that these two are completely independent of each other, and we're going to revisit them later in the lecture. So today's lecture, we're going to look at what happens when you place a superconductor in a magnetic field. So you have a superconductor, you apply a magnetic field, what happens? Now, any idea what happens? Right, and now if you keep ramping up the field, what happens?
At some point you reach critical current.
Yes. So if your field is large enough, it will suppress superconductivity. So first we're going to understand, you know, hopefully understand why we have Meissner effect. What's the mechanism behind it, really? And also, what, more importantly, why do we have critical fields? Why does a magnetic field suppress superconductivity? Any idea why? Well, don't worry, we're going to cover that today. So, and then we're going to also talk about what, you might have heard that there's a type 1 and type 2 superconductor. We're going to, talk about why we have these two types. Although I must say the boundary between these two is a bit blurry, especially when you go to thin films and nanostructures. And then we're going to actually, the fun part, which I hope to get to, is what happens when you have a mesoscopic superconductor. So when you have confinement effect, what happens in a superconductor, what does flux quantization, what do those things look like? So I'm going to give you some of the examples. Right. So this is a phase diagram of a typical superconductor. This field, this temperature, and you see there's a critical TC, there's a critical temperature, and there's also a critical field. Now this is a phase diagram of actually what we call the type 1 superconductor. And and you see above a certain field, you lose your superconductivity. So, any idea how that happens? Why would the superconductor just, why would superconductivity be suppressed when you apply a field? Yes?
Maybe kinetic term becomes too great, so balance it basically becomes significant with the potential that they have for themselves.
Yeah. So where does the kinetic term come from in the first place?
From the magnetic field, we have the motion.
Why would you have a motion because of the magnetic field?
Maybe the magnetic field is perpendicular to the plane that we have to be superconductor and have some cyclic motion.
So this is the motion of, you mean like a current or a supercurrent? Is that what you mean?
Maybe. I'm not sure.
No, you're absolutely right. So you apply a field to a superconductor, it generates a current, a supercurrent. Now, you might say, well, if I do that to a normal metal, that's also the same thing happens. What's the big deal? You get a superconductor, you get a loop. Switch on a magnetic field, there's only a current in this loop. Doesn't have to be superconducting. So, what's the difference between that and a superconductor? Yes?
The superconductor has a critical current that you can't go above.
Sure, but as long as we stay below that, I mean, actually, if you in a superconductor, in a bulk superconductor, your critical field and critical current are actually related. So the reason you have a critical current is because the current that runs through your superconductor, produces its own field, and this field at some point actually, so critical field and critical current are basically the same effect. Not in Josephson junctions, we'll come back to those later, but in a normal superconductor, that's the case. But my question was, what's the difference to a current generated in a normal metal by applying a magnetic field and the supercurrent induced in a superconductor due to an external magnetic field?
Is it voltage?
Well, there is no voltage, so right, but here let's just say, what's the mechanism behind this? What's the difference? Well, the reason I'm actually, kind of lingering on this point so long is because it's a small point, but it's an important one. You see, in a normal metal, your current that you induce in a normal metal is not proportional to magnetic field. It's proportional to what?
Time derivative.
Time derivative, the rate over which you apply that magnetic field or you remove the magnetic field. It's the gradient of the magnetic field. It's a time-dependent derivative of magnetic field. That's what drives normal current there. Here, we're talking about static field. Doesn't matter how slowly or quickly you ramp it up, it's not at all. Not going to change the outcome. So why do we have this current to begin with here? If it's not that, what is it called? I think it's called Lenz's law. If it's not that, so what is this? Well, the answer is because, well, what happens when you apply a field is that the orbital phase of your wave function couples to this external field. So if there is no field, your phase is happy. But the moment you switch on the field, now suddenly you're introducing an orbital phase shift in your wave function. So that means that if you go around in circle, no matter where in your superconductor, in your system, the phase of the order parameter, the phase, needs to wind by 2 pi. It has to be either wind by 0 or 2 pi or 4 pi. Now, but if it's not that, what happens is that it leads to a supercurrent. And that supercurrent obviously has some energy, kinetic energy. So you generate supercurrent, sure, it's dissipationless, but it still costs energy. Now, where does that energy come from? It comes from your condensate. So, your superconducting condensate, your order parameter has a certain energy. Your gap, if you like to think about it, has a certain width, and that you can quantify it in terms of energy. So this Tc of your superconductor, you can directly convert that to energy in electron volt unit. That, when you superconduct it, the supercurrent that you generate when the kinetic term, as you said, reaches the energy of the gap, that's when you lose superconductivity. So you put in kinetic energy, you apply magnetic field, it costs kinetic energy, even though it doesn't dissipate, it costs still in kinetic energy because we're talking about actual charged particles going round. And that kinetic energy basically at some point gets too large, it becomes bigger than the size of your superconducting gap, the energy of your condensate, and you lose your superconductivity. Okay, now this is, type 1, but most of the superconductors belong to category 2, which is called a type 2 superconductor. Now in type 2, it's a similar phase diagram, but there is an extra intermediate region here. So in this case, what happens, you start with just being a fully superconducting state, and then above a certain field, you start letting in magnetic flux, but in quantized units. So what happens in these materials is that part of the superconductor the superconductor becomes like a Swiss cheese. Part of it has these holes in it. And then your magnetic flux can actually go through these holes, but it does it in quantized units. And those units are h over 2e, or magnetic flux quantum. So this is, and the 2 actually is what we have Cooper pairs. But so when you apply a field here in a type 2 superconductor, you start having these little holes, these normal regions, and through this normal region, magnetic flux can penetrate, but flux needs to be quantized in units of phi naught. Clear so far? Yeah? Okay. So this is the formula for upper critical field. Actually, you can derive it. It's quite straightforward. I mean, there's different ways to derive it. I think it's one of your homework questions, but there's a simple way to do it and there's a difficult way to do it. Whatever works for you, I'm fine with it. So this is the upper critical field, and by the way, the important thing I want to say is that this magnetic flux quantum is universal. It's not a unique characteristic of only type 2. Any superconductor, when you pass a flux through it, it has to be unital final. Doesn't matter if it's type 1 or type 2. But why do we have type 1 and type 2? Any idea how that happens? So to put it more specifically, why can some superconductors have vortices and others no, go straight to the normal state? Well, I think that becomes clear if you look at the, let's say, a closer look at what a vortex is. So, as I said, you have a superconductor, and you have these normal regions. These are the core. This is each of them is a core of your vortex, where your superconductivity goes to 0. So if this is the amplitude of your order parameter, within this core, it goes to 0. And around it, you have, because now you let in one magnetic flux quantum, now you need to wind your phase by 2 pi. So what that generates is a supercurrent. So there is a supercurrent working around this normal core, keeping the flux inside, right? Otherwise, the flux will just go everywhere. So you have now a circulating current, and this, has a 1 over r relation. So far away from the core, you don't have any supercurrent, and as you get closer and closer, then you have more and more. And that also means, this is basically exactly, so now if you think about it, the two length scales are very clear what they do here. The normal core, what's the diameter of the normal core? It's the coherence. The diameter is 2 coherence lengths. That's the size of the vortex core. But there's a field around it. Of course, the field needs to be screened by the current. And the characteristic length for that is? Thank you. It's lambda. So far away from the core, there is no field. And as you get closer and closer, you have the field, and this is the relation. So, but here's the question. Why do we have a normal core? Why is it energetically favorable for a superconductor to part of it just go normal? Because as I said, it would actually cost energy to suppress your superconductivity, right? So you need to locally bring the amplitude of your wave function to 0. And that costs energy. So why does it happen? Why is this a stable scenario, energetically speaking? Any idea? Think about the kinetic energy of a vortex. Think about this current. What happens as you get closer and closer and closer to the center of the vortex? Any idea? So this is r, is basically the distance from the center of the vortex. What happens when this goes to 0?
Blows up.
Yeah, it blows up. Your current goes to infinity. Your kinetic term goes to infinity. You have infinite kinetic energy. So what's the solution? To not having supercurrent at all. To just chill your order parameter, and that takes care of it. You see, here your current just keeps going faster and faster and faster until you reach the coherence length. And at that point, the amplitude of the order parameter starts going down. So you can't have infinite supercurrent. You can't have infinite, it becomes suddenly energetically stable. And now this seems like a very much, a straightforward thing today. But solving this problem is what got Abrikosov his Nobel Prize. He actually pitched, he predicted the existence of the vortices, which we now call Abrikosov vortices, and but his PhD supervisor Landau actually didn't believe it. It was like, this is all rubbish, and he actually put it in his drawer, forgot about it. For I think 2 or 3 years later, where he suddenly, for whatever reason, he was like, oh, maybe there is something to it, and then, he actually accepted it. So, because if you don't know about vortices, it seems like a very strange thing that because the current would just go faster and faster and faster. But of course, and Abrikosov came up with a solution that to get rid of that problem, to solve that problem by just killing the amplitude of the order parameter. Okay, so let's go back to the question we had at the beginning. Why do we have type 1 and type 2? What determines if your superconductor is type 1 or type 2?
The coherence length is smaller than the penetration.
Yes. So you can only get vortices if your coherence length is smaller than penetration depth. That's how you stabilize your vortex and don't run into that problem of infinite energy, right? So that's the only way energetically suddenly you can stabilize a vortex. If it was the other way around, it wouldn't work. You wouldn't be able to suppress your supercurrent. Your order parameter is going to be actually bigger. So you letting one flux line in your superconductor, there is no way you can screen it, first of all, because your lambda is actually now smaller than your coherence length. You get what I mean? Is it clear? Just reverse, switch the order of these two, and you see this picture doesn't work anymore. You should tell me if I'm going too fast or it's not clear. Okay, good. Right, so this ratio, lambda penetration depth and coherence length, that's what determines whether you have a type 1 superconductor or a type 2 superconductor. And when you do have a type 2 superconductor, apply magnetic field, you have something like this. This is called the Abrikosov vortex lattice. It's a honeycomb-shaped lattice. Why? Any idea why it looks this triangular lattice? Yes, it's the optimal packing in a 2D system. And why would you, then the question is, why would you have that? Why would vortices try to avoid each other and go for this optimal packing? Try to picture you have a vortex here, you have a vortex here. Yes?
If they get too close, they effectively become one, and the size is fixed by these parameters, so that should be.
So if they get too close, they actually don't become one. If they became one, then the whole thing would be unstable. So what is it that keeps them apart? The currents. Because you have that vortices with the same chirality, with the same current. That's how that's what makes them avoid each other. So they actually repel each other in this case. That's why you have this hexagonal lattice, because of optimal packing, because energetically it's not favorable for supercurrents to overlap. That causes double kinetic energy. So that's how they try to avoid each other. Okay, so this image, by the way, I showed you, is actually taken by, any idea what? Yeah, well, it's already on the slide. This is, I switched too soon. This is an STM image, right? Everybody's familiar with what STM is? So what do you image when you do STM?
density of states.
Electronic density of state. That's what you image, right? So you SEM, you have a tip, you have a sample, you change the bias voltage. Basically now your electron can tunnel to the available states in your sample, or vice versa. You could also tunnel from your sample to the other way around. Now, that's how SEM works, but how do you use that to image vortices? How do you get electron tunneling to see a vortex? Think about the density of state on the sample. What's happening there? If you have a superconducting sample, what's the density of state there? Think about the Fermi level. What happened to the Fermi surface? So for tunneling, you need to go to a state, right? The electron needs to go from one piece to an available state. Are there any available states? Yes.
So you have the gap.
You have the gap. And what happens in the gap? There are no electrons allowed. You don't get tunneling. There's no available states. So, when you do this, this is basically you tune the bias voltage, you change your potential. You have states above and below the superconducting gap, but nothing in between. It would actually appear as if you had an insulator. Right. But it's not empty. It's a full gap. It's just that electrons are not allowed in. So that's the gap. Now, how do you use this to image a vortex? So which part of the vortex can you image with the STM? The core, exactly, because when it goes normal, suddenly there are available states. You can tunnel from your tip to your sample. And that's what you see here. Here, these are the cores, and where your tip can tunnel to the sample, and the darker regions are where you cannot tunnel. They're not available.
What's
Yes.
this scale bar here?
Well, I can tell you roughly what it is. So this is, each core is probably 32 nanometers. Because this is now run by cellular and the coherence length is 16 nanometers, so it has to be 32 nanometers. Yeah.
In zero field.
No. This is with the field. How closely packed they are. Yeah.
Yeah.
Come back. But are there other ways that we could image vortices? Some of you are smiling because we just imaged some yesterday for the first time. And yeah, I'll show you in a bit, but think about other ways that you can image vortices. So yes, one, you can look for them using the electronic signature. Magnetic. Look for the magnetic signal. And funny enough, that's actually the first, evidence of vortices came way before STM. This is called, this is from 1967, way before STM. And this is called beta decoration. So some of you might know this, but basically what you do is a very clever technique. So you have a superconductor, you apply a magnetic field, and you have this, of course, flux line wherever there is a vortex. And what you do is that you get a very fine magnetic powder, and you spray it into your chamber. And these fine powders, these magnetic particles, basically fall onto your sample, but because they're magnetic, they follow the field lines. So you get a higher density of these magnetic particles where you had a vortex. And then what you do is that you warm it up. Of course, this is a room temperature image. You look at it in a scanning electron microscope and you see, this nice pattern. So this was actually the first image of, vortex lattice. And it was, they done it with this technique. Pretty good if you think about it, So too bad it only worked, you have to warm up your sample to look at it at room temperature, but otherwise it's a very, resolution-wise and so on. Pretty impressive. But of course, there's more sophisticated techniques now these days. One is the scanning-SQUID. We'll visit this later in the lecture, but basically what you have is that you have a superconducting sensor, it's called a SQUID, and normally in scanning-SQUID you have a pickup loop, so there's a loop that comes out, and the flux inside here is what the SQUID measures. So the SQUID is far away, and there's a loop, and whatever flux that runs through this loop changes the voltage and currents in the SQUID, and you can image. So here you're seeing the vortices in a high-temperature superconductor, which you would not actually be able to see with STM. So it's very hard to see vortices in a cuprate superconductor with STM. Well, because generally STM is very difficult in these materials, and secondly, your coherence length is like 3 angstrom, 4 angstrom. So very, just to give you put things in perspective, coherence length that in the previous slide was 16 nanometer, so 12 nanometer. So now you go to below 1 nanometer coherence length, plus other, problems with cuprates. That's gets really difficult. But here you can image them magnetically. Yes.
This feels at 100 micrometers.
Yeah. Yeah.
So they're massive.
So that's a good point. Yes, this is actually funny. I sometimes say that you could probably see this, with the naked eye. Maybe this is such a large scale. The reason is partly because scanning-SQUID usually the resolution is about, best case is about 4 or 5 microns. And secondly, in this case, what they've done is that this is pulled down at 0 magnetic field. So basically what you're imaging is like vortices due to Earth's magnetic field. That's how much field it takes to induce all these vortices. And there you see the spacing is nowhere near as closely packed as the Abrikosov vortex lattice shown here. So this is very sparse, diluted. There's a spacing is like we're talking about, 20 microns between, 50 microns between each vortex. Now, there is an upgrade. There is a thing called the SQUID on tip. This is what we've developed with some of you actually in the room. So here, instead of putting the SQUID file, somewhere away, you put the SQUID, the sensor, right at the tip of your probe. And this is what you get. So you get a much better sensitivity and much better resolution. And this is actually our first image of vortices, which came out only yesterday. So I'm very excited about it. I mean, it actually turned out to be, imaging vortices turned out to be way harder than I thought. And it turned out that it doesn't take that much field to induce a ton of vortices in your system. So a lot of time we were actually applying the field and looking for where the vortices were, but they were actually everywhere. So so this is what they look like. So they're real. Good. Now, how are we doing with time? Okay, we're not doing so bad. Yes.
Is it ever possible to image like the donut shape that you have from Abrikosov vortex with the highest current looping, or is it?
Okay. So I was not sure what you mean by the donut shape.
So here you have like the intensity of the core, right?
Yeah.
And you have that in the lattice, but do you think it's ever going to be possible to image the actual radius of the highest flowing current? So this basically what the image is the field that comes out. Yeah.
So this is a current distribution.
Yeah.
And here what you're imaging is the field.
Yeah.
And that's what we do with the SQUID on tip.
Yeah.
So I don't know if I understand correctly.
So you have these concentric circles,
Yes.
and some of them are brighter, some are darker. Do you think it's possible to resolve with some?
Oh, you mean that we go high, low?
Yeah.
Well, no, you wouldn't be low because your field would just go up.
Okay.
So this is just a distribution of the current. But the thing that you measure with the SQUID or SQUID on tip is the distribution of the field, and the field is going to be maximum at the center, so it won't have this downturn. Yeah.
Unless you find a way to image the current directly.
Yes.
Should
Yeah, I'm sure.
Yeah. Should be
Okay.
possible to measure current as well.
Good. I'm up for it. You know, with some ideas, I'm all ears. Yes, please do. So, why not? Yeah. Good. So, yeah. So this is basically more or less what I wanted to say about vortices in bulk material films. Now, I want to move on to more interesting problems, which is basically about flux quantization not in film, not in bulk materials, but in mesoscopic structures. Because this is where you kind of really get the true feeling of what your superconductor is doing. It's way more, let's say, exotic than just expelling magnetic field or having vortices. And you see why. Actually, I think last lecture I ended with a question of, is it true that a superconductor would always expel a magnetic field, or are there also exceptions? So you probably see what I meant by that in a few minutes. So before we take a break, I wanted to play let's go to the game. We're going to play a game. We're going to try to predict what a superconducting ring does. So I want you to kind of imagine that you have a superconducting ring, right? And you need to, and somebody puts you in a magnetic field, right? So you have a ring, and of course now, for the sake of the argument, say this is a very thin-walled ring, so it's much, smaller than the coherence length and the penetration depth, so you can forget about any screening within the ring itself, right? And so you're below, your dimensions of the ring is actually smaller than the coherence length and the penetration depth. Now, there's two rules here basically. The first one is that your phase, so when you switch on the magnetic field, so what we're going to do here is we're going to switch on the magnetic field and look at what happens to the supercurrents. So when you apply a magnetic field, as we said, it generates a supercurrent. We're going to try to plot that supercurrent as a function of magnetic flux. Now there are two rules. One is that the flux inside the ring needs to be in units of phi naught, which basically is same as saying that the phase of the order parameter needs to wind by multiples of 2 pi. So that if, for instance, you have at 0 field and at 1 and 2, you have no supercurrent. Your supercurrent is actually, there's no reason to have a supercurrent. Because the only reason that you have this supercurrent is to compensate for this phase shift introduced by the magnetic flux. And in this case, you have no Meissner screen, so your superconductor doesn't care. It actually has it generates no supercurrent in this case. Is that clear? Okay. The other rule is that the circulating current, one thing you should remember is that the energy associated with the circulating current needs to be minimized. Right? As I said, there is no free energy, and if you're putting, despite being dissipationless, when you have a supercurrent, it costs energy, it costs kinetic energy. So your superconductor tries to minimize that as much as possible while satisfying this goal. So this is the two things you need to satisfy. So we apply a bit of magnetic field. Right, this is, let's say, 1, this is half. We go up the way here. We get some supercurrent in our system. Okay? So far, so good. Now, what happens if I increase the field? Yeah, you get more current in your loop. There's more supercurrent there going round and round. And let's go even further. What happens is that you keep applying the field, and your supercurrent works against it. So you put more flux, your supercurrent has to work harder, it has to go faster, and that costs more energy, but that's what it does. So far, if you're sitting here, what's the flux inside this ring?
Zero.
Zero, yes, because of the supercurrent, it's been compensating, all right? So, what happens next? What happens if I increase the current further?
It will turn the other way.
It will turn the other way. Why? Why not just keep going?
Because now we reach pi.
Yeah, but it needs to be 2 pi. So actually pi is the least favorable situation for it. So why would it, so you mean that it would turn the other way? So you, like basically you mean that your current would start going the other opposite direction. Okay? But why not just keep canceling the field? I mean, you're right, absolutely, right. So you're absolutely right, it does. Actually, so far, it's been working against the field, but now that it's going is at maximum velocity, suddenly it switches direction. It goes the opposite way, and now as you approach more to go to one fluxoid, actually slows down. So right here, when it was going is at fastest, so far it was canceling out the field, and at this point he says, you know what, screw this, I'm going to actually allow one magnetic flux to enter and help that. So you basically, up to this point, it was canceling the field, now it's helping the field. It's amplifying the field, the external field, to bring it to one flux quantum. And I think that's a good example to show that it's really not just about, superconductors are allergic to magnetic flux. No, all they care about is the macroscopic wave function and the phase, which needs to wind continuously. And either they can get there by canceling the field or helping the field. So it can go either way. And of course, if you keep increasing, your field, so this is a kind of a pattern you get. Now, how do you measure this? This is, yes?
I'm just thinking how the flux inside the loop now, how that graph looks like.
Okay, good. Yes, so
That's zero for some time.
This is 0, now you have 1, then you have
0.
1 again, so this is all 1, then you have 2. So once you pass this halfway, you add 1. So
Right.
0, 1,
Okay, so it's increasing only.
Yes.
Right? It's multiplying.
yeah.
Okay,
So the
but
flux
step
keeps
one.
increasing. Yes, yes.
Right.
Yeah. Very good. All right then. Now, well, this actually is just another thought experiment. They measured this. It was a very important experiment. It's called the little parts experiment. And how do you measure it? Well, basically, this current that we talked about, as I said, it has kinetic energy. So that's kinetic energy proportional to J squared. And this kinetic energy has to be taken away from the energy of your condensate. And what does that do to your transition temperature? It lowers it. So the more, where you have maximum current, you have maximum kinetic energy, and you have minimum TC, your transition temperature of superconductor is minimum. So here you can think about as your condensate, the energy, let's say the gap going, rocking a little bit back and forth. So this is where your gap gets smaller, your superconductor has less energy, and more energy, less energy, more energy, all because of this kinetic energy associated with the supercurrent. Okay? Now, if you want to measure this, where do you measure it? Well, you want to measure TC, you need to be at the transition. So what you look at is you look at the resistance measurement. So you do a magnetoresistance measurement, and the way to do it is that if this is your transition curve, of course, there's a bit of a period before superconductor goes from normal to superconducting. So you park your temperature right here, and now if the transition temperature goes down, suddenly your resistance goes up, and as the transition temperature goes back up again, resistance goes down. So it ends up looking exactly like basically what your kinetic energy looked like. So these are called little Parkes oscillations, and they're still relevant to this day. So we still use this experiment for a lot of things to show, for instance, the kind of symmetry we have in superconductors. It's a very good technique, and you'll see why, because for one thing, actually, it's a phase-sensitive measurement, but I'll show you some more examples later. But this is actually the plot from the original paper from 1962. This is the screenshot they had. And this was a big deal when it came out, because this was one of the first, actually there was only one other experiment which was not also as nice, but this was basically the one experiment that established that you have Cooper pairs. Why? Because you have 2E here. What would be the period if you had just very good electrons? Would be H over E. It would be twice as much. So this H over 2E was a big deal at the time because it was actually the thing that really, without that, established that Dean Cooper pairs. Now, you'll notice there's a bit of a parabolic background here, right? Which I conveniently ignored in the last slide, but you see that there is a kind of a parabolic shaped background in both TC. And we'll come back to this after the break, but very quickly I want to show you one thing. We brushed over this, but I want you to think about what actually happens right here, right where this dotted line is. Suppose you could apply a field that is exactly phi naught divided by 2, and you start with a normal state, right? And then you cool down your superconductor, right? Which way is the current going to go? If you're exactly halfway.
Both ways.
Going both ways? Okay.
Or no current?
Well, no current is going to be a problem, huh? Because if you have no current, then your phase is just not going to wind.
Superposition?
Yes, you both. It's exactly right. Right here, your supercurrent is going both ways. Right when it's at its maximum, it's both winding clockwise and counterclockwise. It's in superposition of both of those. This is a qubit. And this is how we actually make superconducting. A lot of the superconducting qubits, like transmons and so on, they actually use this concept. Well, of course, they don't just use a ring. That's not the most practical way, but you can literally create this scenario that your phase is winding by exactly 1 pi in a loop, and then you end up with a superposition of clockwise and counterclockwise till you measure it. And there's different ways. One of them is actually, there's different ways you could do this, but let's say one that we will visit later in the course is by putting a pi junction here. So here, for instance, you interrupt this superconducting loop with a very thin ferromagnetic layer that creates the pi phase shift. And that pi phase shift is exactly equivalent to bringing your system halfway between 0 and phi naught. So you have pi here, and you wind here, you need to wind by 2 pi, and you also wind here by to get to 2 pi. So in that case, you also create a superposition. Therefore, your current is going in both directions. Till you measure it, of course. Then it becomes one or the other. Okay, with that, let's just take a break. Yeah. Okay. Right. Now for the rest of the lecture, we're gonna for the rest of the lecture we're gonna move on to mesoscopic systems. Right. And yep. So one thing that specifically I briefly mentioned it in the last before the lecture before the break was this parabolic background in the little Prox measurements. That's actually a real thing. So the interesting thing about superconductors is that when you confine them, when you reduce your dimension, and suddenly the superconductor actually becomes more robust against magnetic field. So here, for instance, showing you the critical field and critical temperature of a bulk superconductor. This is aluminum, this is for bulk aluminium, and this is for a nanowire, 150 nanometer wide wire of aluminium. And you see it has this parabolic shape and also much higher critical field compared to bulk. Now, what is this? Well, this is something that, let's say, you get this enhancement when you're in a so-called London limit. And what's a London limit? Now, this is where your order parameter, your wave function, has a constant amplitude throughout your system. So imagine if your system is so small that you reduce dimensions to a point where you can't change, you can't vary, the amplitude of your order parameter anymore. That's where you have London limits. So when we're talking about this, we're talking about systems where the dimensions reduce so much that there are no variations in the amplitude of the order parameter. And so there is a bit of a crossover. So you see here, there's a tiny wire, and this is the loop. You see it has the little Prox oscillation we talked about on top of this background. And here we have a disk which is somewhere in between. So there's actually a crossover going from a 1D superconductor, so that's what the London limit is, and a 2D superconductor. And in 1D, you end up being, having a higher critical field because of confinement effects. Now, the reason for this is that, first of all, I'll come back to that in a second, but the reason is that actually you save a lot of energy when you go in this 1D limit. But first, let's think about what it means to be 1D. So how mesoscopic does your system need to be in order to be in this limit? How small does, for instance, the width of this wire need to be for it to show this parabolic behavior and a higher critical field?
Smaller than the coherence.
Yes. So when you go close to the coherence length, when you approach that, you approach the London limit. But this is actually important to note is that the coherence length, if you remember, is temperature dependent. So if, let's say, and you can see what happens when you go close to TC. Any idea what happens to this value, to the coherence length? When you approach TC? Divergence, it shoots up. So even when your coherence length, for instance, is 10 nanometer, when you're at the boundary, when you're close to the transition temperature, it could be 100 nanometer. And then you could end up you will end up in the London limit. You end up in a regime where your confinement effects actually kick in, and you have a higher of a critical field. And so the question is how, yeah, we'll come to that in a second, but what about a thin film? Suppose you have a thin film, suppose it's actually thinner than, you know, your coherence length. So your coherence length is, I don't know, 10 nanometer, and this film is also 10 nanometer. What about this one? What's going to be what does the phase diagram of this thin film going to look like? Any guesses? Well, let me put it this way. Suppose you have a thin film, very thin film, and you apply it at a plane magnetic field. Which scenario is going to happen? Are you going to get this, or are you going to get that? Or something in the middle? Any guesses?
No.
Both. Why?
Because in the plane there's no limitations in terms of
There's nothing
size.
confining it. Yes. So here, actually, you have vortices. You have supercurrents going around. The stuff that costs energy. See, the reason why this critical field is so high is because you can't have. You basically suppress all the mechanisms that would cost energy for your superconductors. You have no normal cores. You also don't have room for your orbital currents, your supercurrents. So you basically save a lot of energy by confining your structure. So if there is no room, if your superconductor is 1D, it can't have this 2D orbital motion. Cooper pairs can't have that, and therefore you save a lot of kinetic energy. And you save the kinetic energy, that shoots up your critical field. It's a bit, maybe, counterintuitive that making something smaller, it actually becomes more robust. Because it doesn't have room to waste its energy on, I don't know, vortices and orbital angular momentum of Cooper pairs. But what if we apply a field now in plane? What about then?
Shouldn't be any supercurrents because it's thinner than the coherence length.
So what happens to your, which one is it? Is it going to be this picture or this picture? Anyone?
On the left.
Sorry, what do you mean? It's going to be like both?
No.
It's going to be like this?
Mm-hmm.
Going to be, right? Who else thinks that way? Raise your hand if you think it's going to behave like a 1D superconductor. Okay? Raise your hand if you think it's going to behave like a bulk superconductor. Okay, nobody raised their hand. So, well, then I guess there are a lot of undecided. I see, but it's actually identical to this wire, because it doesn't matter how big or small this film is. What you care about is this dimension. You see, you apply the field, you care about the dimensions according to what the vector potential in that direction is, right? If you're applying the field this way and you have no room for supercurrents, no room for that, that's how you save your kinetic energy. That's why a thin film in plane field is going to be identical to having a nanowire. Yes.
Is this blip in a real at the very end?
No, that's not a real thing. I don't know what that is.
Okay, that's not some London Park special.
No.
Too bad.
Yeah. So I don't know. Sometimes things have blips and people don't talk about it.
Sorry.
It's all right. Yeah. All right, good. No, it could have been something, but this time, I don't know what it is. Yeah. So, okay, but in the homework, we're gonna get a little bit deeper on why, how you. I mean, I think we more or less covered it, but there's also a homework question about this: why you actually save energy and why you have a high critical field when you go in a confined structure. Okay. Now let's go back to superconducting loops, right? We saw how, you guys saw how if you have a single loop and you apply a field, you get these little Parks oscillations. Now what if instead of one loop you have two loops? What's going to happen there? So first of all, let's put it this way. Would you still see lower Parks oscillation? Who says yes? Okay, who says no? I mean, there's nothing at stake here, guys. You could either, seriously, you could either say yes or no. I don't care if you're wrong, but stick with one of them. Should make a decision. Are you gonna see oscillations? Yes? Okay. No? Anybody says no? You say no?
Sure, but
Very brave. Why? Why do you think no?
you just said big one.
Oh, okay, fair enough. I did push you there, didn't I? Yes, that was a trap. I can come for it. Good, but I'm glad you made a stand. Takes courage, yes. But unfortunately, it's not true. You do see oscillations, and actually it's exactly the same as what you would expect for a single loop. Why? Because all your loops have the same dimensions. So if each of them is changing its resistance, or TC and resistance, they're going to all go up and down at the same time if they're the same dimensions. So in that case, your measurement is going to look identical to what it would be if this was a single loop, right? So double loop, you get the same little Parks oscillation as you would for a single. Actually, for one time we wanted to make sure we have enough signal, so we made, I think, about 50 of those loops and connected them, and signal was pretty decent. So this is one way to do it. Yes.
So can you please maybe repeat where does the oscillation come from again?
Mm-hmm. No problem. The oscillations come from the current induced by the flux. So you sweep the flux, there is this current going up and down, like we talked about. And that current is kinetic energy, which needs to be subtracted from the energy of your superconductor, which means that your TC, which basically characterizes the energy of the superconductor, oscillates back and forth. So in the plot that I'm showing you, basically TC is just that it's a little bit, it's tilted by 90 degrees as a function of field. So, yeah.
So, just in practical terms, where does then the energy come from? Because you say your TC is lower or higher, sure.
Yeah.
But in your experiment, you have this device.
Mm-hmm.
It's superconducting, showing these oscillations.
Mm-hmm.
But there's no dissipative
No.
mechanism. So where does the energy come from?
So your question, how does this not violate?
The supercurrent is running,
Yes.
and you say the energy to do that comes from the temperature.
So the kinetic energy subtracted from the energy of your wave function, or the parameter, whatever you call it.
Yes, but then I would sort of naively in my head connect that to, then my cryostat needs to work a little bit harder, but that's not the case.
No.
So then,
Because within a superconductor there is no thermal gradient.
right.
So you're not measuring thermal
No.
temperature. There's no temperature heat being produced.
Sure.
There's no energy lost or created here. It's just that because this is a supercurrent after all. So it doesn't, you're not basically, there is no dissipation at the end.
So we're not actually generating any. Yeah, right.
No.
Okay.
So you're varying the field, yeah. You're applying the field, and then you're getting, just wait till I tell you about phase batteries. That's a whole other crazy thing. It's like a battery for normal electronics, but it just for superconductors, and it never runs out because,
It's all free.
it almost feels like your perpetual motion, but it's not. It's actually, it's at the end of the day, you can't extract any energy from it.
Yeah.
So that's the whole point.
That's it.
Because, yes. So, is it clear why we have oscillations now? Is that the, right. Now, going back here. So, these loops, we saw these oscillations. Now, let's make it a bit more interesting. Let's make it like this. Let's make a double loop. What do you think is going to happen now? Think about what's going to happen with the currents, right? So here you apply a field, there's a current running in each of them, right? Now, what if they share one side?
There's one more current.
Hmm?
There's one more current on the outer.
Right, so in that case, is it going to be the same as the other picture? I think, yeah, it looks like nobody agrees. Everybody thinks it's different. And you're all absolutely right. The oscillations do look different. You see, you have your oscillation, but then there is this peak right at the boundary between these two. So here you have 0 fluxoid, 1 fluxoid, but right in the middle, there's this little blip. Well, to understand what's going on, let's have a closer look at both of these cases. What's happening in terms of magnetic flux that enters your loop. So, this case, you're looking at 0 field halfway and 1, right? So this is, on this side of the first oscillation, you start at 0, you have 0 magnetic flux in either of those rings. So the 0, 0, right? You could think of it as no vortices. A vortex, you could also think of these as vortices. It's actually useful. It's just not an Abrikosov vortex. Any time that you wind your phase by 2 pi to have a fluxoid in a system, that's a vortex, basically. By definition, vortex is just winding the phase by 2 pi. So here you have no vortices down. Here you have 1, 1. So that's what it looks like. But in this case, there's this little blip. Well, you could break it down into 3 regimes. You say that on this right side you have 0 vortex, just like the previous case, and now you have a vortex in each loop. But what's happening here? Right, this is the, why do we have this blip? Yes.
That's in a big loop. Just ignore the middle.
You ignore the middle part? Can you ignore the middle part?
Not really, so it's a little bit.
So let me put it this way. If you just follow the London limit, which you think, well, this is what should happen, you are in that limit, what you're going to get is, well, either vortex in one or the other. But actually, symmetry-wise, in terms of topology, that's yeah, but it's also not going to help your problem because at the end of the day, these states are just not stable. Like if you're exactly at half, where is this vortex going to be? In the left one or right one? How does it choose? That's one problem. The other one is, what about the supercurrent? Just think about the screening currents that are actually going in each loop. This middle part is going to go, well, you're going to have a problem there. I think you can think about this a bit more if you want. But, so what happens is that neither of those. But, you actually came pretty close. What does happen is that you get one vortex shared between both of these loops. And the way you can do that is by suppressing the order parameter, by killing your superconductivity right in this middle region. So this way, you can think of it as a vortex constantly being in the superposition of both of these. You can actually, you see vortices you'll see later, they seem like this abstract thing, but now, you know, the way I would describe it is that you have a vortex, it has a wave function that spreads on both sides and it actually tunnels through this barrier, and that's how you get a normal region. Now that might sound just like nonsense, but hopefully I'll give you some example of when and how that happened. But even in this case, actually, this is, you know, Parkes already kind of predicted this is what would happen in this geometry way before they saw it experimentally. Your superconductivity is just the amplitude of your order parameter goes to 0. You create a normal region here just so that you can basically, just for the reasons of topology and also being saving energy. Because otherwise you would have double supercurrent in this middle part. So it becomes more energetically favorable to suddenly create a normal piece here and let the vortex be shared between both loops. And this can be even in type 1 superconductor. Aluminium is a type 1 superconductor, but you can really think of this as a vortex crossing this middle part. Yes?
And this again was 30 years before Meissner?
I think 20, I think a bunch of people tried it, but it's pretty much, yeah. It's the same Parkes as little Parkes.
Right.
Yes.
So what is the current doing now? Like,
So now, in this case, the current is just going on outer loop. There is no supercurrent going in the middle part because there's normal region in the middle. So, you know, so in a way, this is actually kind of really, it's a recurring thing with superconductors. It's not something that you could, whatever is respect to symmetries actually come first. And then secondly, energy, that's the thing that actually, you know, minimizes your energy, that's the thing that happens. So if you, you know, commit to any specific framework or say, oh, I'm only going to do Green-Book lambda, or use the Dell equations and just let the computer run its course and give me the answer, that's where you're going to run into trouble because, well, you know, the superconductors are full of surprises like this. So in this case, even if you go far below the transition, this is the crazy thing, even if you go, you cool down your system in this region, apply this field and cool down and you go, you know, 1% of your TC. So when you're fully superconducting state, this part would refuse to be normal. It would refuse to be superconducting. It would actually remain normal regardless of how low you go in temperature. But here's even where it gets even more crazy. It's normal, but that doesn't always mean that there are no Cooper pairs. You could be, basically what happens is that you have incoherent Cooper pairs. You have a vortex constantly crossing this line and disrupting the phase coherence. This is called phase slip. So, in this case, even if you have Cooper pairs, even if you go with a STM and measure the gap here, you should see the gap, but well, not the gap. Sorry, but if you do shot noise experiment where you can see Cooper pairs, it gives you measure 2E, but you would not get. It would still be incoherent. We'll come back to incoherent Cooper pairs later, of course. Okay, so I want to end with one last example. It's actually going back to a single loop, right? So this is same setup as the little Parkes experiment. You have current going from here to here, and now what you're going to do is that you're going to measure the voltage between these two contacts. So you're measuring basically this red part. What do you see? Well, this is what you get. You get this your usual little pulse oscillations, and you could fit this. It's very easy to do. This is the formula for it. It has two components. One, this red part corresponds to the integer multiples of flux quantum entering the system. So L here stands for lowest Landau level. Basically, it's just you can think of it as your quantized orbital angular momentum in this case, in a way. So whatever, and if you solve this equation for L equals 0, 1, 2, 3, you're going to end up with a bunch of lines here, and whichever has the lowest energy is the one that happens. Actually, you see better figures of showing of these plots in Moschalko's book, but it's a very straightforward fit you could do. But at the same time, there's also this parabolic background we talked about. So this is the second part. This is the parabolic background. So yeah, this is what happens if this was just a Y, right? So you would get this no oscillation, right? You would just get your parabolic background. Well, let's see if that actually does happen. So what we're going to do here, we're going to change the measurement, set up a configuration a little bit. Instead of passing the current from here to here and only measuring the ring, what we're going to do is we're going to measure the voltage between this part. So not the ring, we're not passing current here to here, and we're only probing this segment, right? Is that clear? Have you guys seen 4-point measurements before? This is a 4-probe measurement. Basically, it's a way to get rid of all your everything. You only measure what's between the voltage probes, right? Like when there's a current. So, in this case, what would you expect? Well, you expect to have nothing here. There's no loop, right? So, what should we see? Well, you think that, but that's not what happens. You still, the lower an amplitude, but you still see these little pulse oscillations. So there is a non-local effect here that is, you can't explain this with the normal electronics. You have a bunch of systems, you could connect them in series. So here, why on earth would something that happens here affect something so non-local? Any idea?
There's some voltage difference.
No, it's not really bad. So what you're measuring here is not really related to voltage, or what you measure in this plot is TC. It's the transition temperature of this segment, not a voltage really.
Yeah, so there's a bit more current there.
But why? I mean, the current and voltage, these things they're not changing. The only thing that is changing, this plot is showing you, is the transition temperature of your superconductor. Now, we saw how for little pulse you could expect this transition temperature to go up and down, but for this segment to change its transition temperature despite having no current running through it, because remember the reason this thing was basically running, lowering and is TC and TC oscillating, was because of this kinetic term, right? So why would change in variation in your TC, which is like variation in your gap, be observed here? That's what is happening. It's not really a matter of voltage in current or having some electronic artifact. Was there a question? Sorry.
The current still runs through the device.
Yeah.
So that's still susceptible to these oscillations?
No. The reason is because remember what we talked about in terms of length scale? That there are two important length scales, right? One was the penetration depth, but the other one was coherence length. Now, what happens when you get lower in TC? Well, the amplitude of the order parameter goes down. And in this case, this is a very strange thing about aluminium. Aluminium has the largest coherence length of all superconductors. It's freakishly large. It's like basically 1 or 2 microns. So in this case, when your gap, when your condensate gets weaker in the ring, that's not where the wave function ends. It actually, the wave function spreads way beyond that ring. So here, it also lowers the transition temperature of these parts because, again, the amplitude of the condensate, you know, the density of Cooper pairs, the size of the gap, these are all very much related. So when this one, when the ring lowers its TC, it also lowers the TC of this ring, of these leads. Yes?
Is that why lower in the graph we see the peaks clearer and higher it looks more like a parabola?
I think that's because your signal is just weaker. Yes. I mean, generally, even here, you see this just becomes more. And actually, I do recommend looking up this paper. It's also, I provide the link in the homework. It's a cool paper that where they show, they actually vary the length scale here, go, you know, larger and larger, and you see the amplitude gets smaller and smaller. And remember, this is aluminium, so it already has a really large coherence length, and you're also very close to the transition temperature. So that's why you wait, you know, you can have this such a large non-local effect, because your superconductivity here, the order parameter here, if this one changes, goes up and down, it also affects what's around it, because it has to vary over the length scale of your coherence length. Now, if this was any other superconductor, if it was actually niobium, then your coherence length is like 13 nanometers. Well, then you really need to make things a lot smaller. So that's basically something to watch out for, because back in the 80s, 90s, aluminium, even to this day, aluminium is like is the gold standard of all these superconducting. You know, there was a lot of work on mesoscopic superconductors, and unfortunately, in a way, that they all use aluminium. And a lot of the effects now people think is universal, but it's actually just a, you know, a freakish artifact of aluminium having such a large coherence length. But still, I think it's pretty cool. I think it kind of shows how, you know, what it means to have a macroscopic wave function. Yes.
If this was not such a short structure, if it was taller, it was, say, a cylinder, would it still be the same?
It would be exactly the same. Yeah.
Okay.
Yeah. Because actually the original little parts was not, this was, you know, in the 60s, they didn't have nanofabrication and thin films. So you know what they did? They got a glass tube and they evaporated, I think it was lead or tin, I keep forgetting, I think it was tin. Tin on this glass tube while rotating it by hand.
Okay.
And that way they get a thin wall superconductor, you know, cylinder up, you know, around this glass tube, and that's what they used for, that's what they contacted and measured TC and saw the oscillation. It wasn't a thin film.
Okay.
Yeah. So in this case, really for superconductors, the dimension that matters is the dimension that is you know, perpendicular to your magnetic field. If your magnetic field is going this way, you should think about reduce the system to 2D with respect to the applied magnetic field. Most cases, that's perfectly fine. Yeah. You really don't need to worry about what's down there. Yeah. Because all the Cooper pairs, everything needs to wind their phase through the cylinder as it is. And that's why also when you have a vortex in the superconductor, this vortex is not just here, it goes, pierces all the way through your superconductor. Doesn't matter if it's, you know, 10 nanometer or, you know, 5 centimeters, that's what happens. And that's how actually you get levitating trains and stuff because of all these vortices piercing through the system. And they can bend a little bit, but that's what happens. Yeah. Okay, I think with that we're pretty much. Yes, we're end of the lecture. Okay. There will be one exercise sheet online. I think we covered everything. So today, so you shouldn't have any problem handing it in. There is no strict deadline for it, but for your sake and our sake, try to do it within a week. You know, I mean, if it's a couple of days, you know, too late or early, it's fine for us. But don't leave it too late because before you know it, there's another exercise sheet. And I intentionally leave a lot of stuff for the exercise sheet. I don't cover them in the lecture because the important stuff I think is better that you figure it out for yourself. So, yeah. All right.